Yeah.
About ready, Mother Minute?
Oh wait, is it two? No. I'm just gonna leave it two. Do you have to show moving it over? Yes.
Yeah, probably. No, so this one you could go either way. You didn't have to. We'll talk about that in a second. Are we ready for the first one?
Yeah.
Okay. Did you, for your u column, make x squared gradually going away to 0?
Yes.
And dv e to the x constantly. Okay, the first product is on a slant because in the integration by parts formula it's uv. This is u, but v comes after integrating once, so that's v. I understand what I was saying, but there are times we don't know. So, x squared e to the x is my first. After that I would get a negative, and the next product then is negative 2x e to the x. Yes? After that I'd have a negative of a negative, two nested negatives, and that would be a positive 2e to the x plus c. How'd that go? Okay. The other one, on circular it really doesn't matter which you make which. I make my choice based on I'd rather take derivatives of the trig with a chain rule than antiderivatives, but it's your call. So uv, if you do it that way, then uv would be e to the x sine of 2x minus v to u is 2 e to the x cosine of 2x. And our goal is to eventually get an integral here that's identical to the one we started with. We're not there yet, so you have to do this twice, right? So now I'm going to let u, now you have to be consistent. If you let u equal trig before, then you should let u equal trig again. So if u is cosine of 2x, then dv is negative 2 sine of 2x. And if dv is 2e to the x, then v is 2e to the x. You work out the 2 any which way you want, as long as you're careful with it. E to the x sine of 2x minus brackets uv is 2e to the x cosine of 2x minus v to u is now negative 4 e to the x sine of 2x. Alrighty. When I distribute, this side's cool, and e to the x sine of 2x minus 2e to the x cosine of 2x. When I distribute, overall this guy would be positive or negative? Negative. I have 3 negatives there. So it would be negative, so that when you move it over, I'd have a 5 e to the x. I skipped a step, but you can show it if you like. Do you agree that you move it over and with a positive 4 and get 5 total? Okay, so our answer then will probably have a 1/5 in it. 1/5 of e to the x sine of 2x minus 2e to the x cosine of 2x. Let's see. Do you win? Oh, you lose. All right then. Let's go to vector valued functions. What? Oh, somebody say, oh, what is that?
I don't like that.
Check yourself. All right. Here we go. Here we go.
Actually, excuse me, I feel threatened in math class.
Yeah, you should. I could go off anytime. All right. Best beware. We've done vectors of constants, like, hey, there's vector v, it's horizontally 3 and vertically 5, or hey, there's vector u, it's horizontally 2. Are you cutting his head? I cut there. I'll just take your word for it. How's that? U is, well, I just totally lost my train of thought. Whatever, you get the idea. Vectors of constants, that's where I was at. Well, forces don't have to stay constant. They can vary over time. And so you will sometimes see vectors that have functions in them instead of constants. These are called vector-valued functions. For example, v could just have some horizontal function of time or vertical function of time, or both. Or u might be 2 sine t plus 3t. Either way, it's vectors of time, all right? Now, you'll find that in terms of overlap, probably 90, maybe even 95% overlap with parametric. It's very, very similar, you'll see. But there are small differences, and in order to make sure you understand the differences, this is what these two examples are about. Say you had parametric equations like that, over 0 to 4. At time 0, what x and y am I at? Negative 1, 4. Now that is a point on the path of travel, so I could put a point there. At time equal 1, I would have the coordinates 0, 3, time 2, 1, 2, time 3, 2, 1, and time 4, 3, 0. Okay? Now, hopefully you're one of the lucky few that is no longer a knucklehead and remembers that when you graph parametric, you show direction. Hard-earned knowledge, it went that way. All right. Now, compare this to something very similar. The vector-valued function v. In this case, v doesn't stand for velocity. It's just v. That's its name. Okay. Sometimes, though, you'll have vectors have velocity. We'll talk about that in a minute. But the components are very similar. Horizontal component is t minus 1. Vertical component is 4 minus t. And so there will be a lot of similarities here. When time equals 0, what do you get? Negative 1/4. Now here's the difference. Is that point negative 1/4? That's vector negative 1/4. This is a vector function. When you get negative 1/4, that's a vector negative 1/4, not a point negative 1/4. And so you would show that by saying, here's, assuming we start at the origin, we're going to go to that point. Okay? Then when time equals 1, I would get the point, not point 0, 3, the vector 0, 3. And that would be here. At time equal 2, I would get the vector 1, 2. Here. Time equal 3, vector 2, 1. And at time equal 4, vector 3, 0. Horizontally 3, vertically none. Here. Well then, you can see if you were to take the tips of each of these vectors, or the heads, they would still describe that same path, so there is similarity, but they're all vectors instead of points. You follow? They can describe movement. If you describe this as position or velocity, then it would describe movement. They didn't really say it was movement, it was just some vector v. So I'm going to just leave it at that and not necessarily show direction. Are you with me? Are you with me?
Yeah.
Okay. So parametric, you get points on a path. Vectors, you get vectors. I mean, it's a vector function, you're getting vectors out. Let's move on then. Now, because the vectors are not constant anymore, they're going to vary. And because they vary, we might talk about how they vary, or how fast they vary, which is to say we'll do calculus on these vectors. Say you had the vector f described that way. And I wanted f prime. Well, it's really pretty easy. I just want to know how the horizontal and vertical components are changing. So if I want f prime, the vector f's derivatives, I just take each derivative of each point. vector f's derivative is still a vector. The derivative of a vector is a vector. And the derivative of the horizontal component is 6t cosine of 3t squared and 1 over 2 roots of 4 plus t. Other textbooks don't ask this a lot, but our textbook does. They ask for the domain. Now, the domain of the derivative. Consider, first of all, you can't have a derivative at a point that wasn't on the original to begin with. You know what I'm saying? So in terms of the domain of the origin, we're actually going to have to do 4 domains. For the original function, was there any restriction on domain? On t? T is all reals, yeah? For the original function y, is there a restriction on domain? Greater than or equal to -4, yay? What about on domain of f prime? I think you'll agree still no restriction there. But what about y now? Strictly greater than -4, not equal to anymore because of the domain issue. Altogether then, I can't say, you could use this time for this guy, but this time for this. When I put in a time, I put it in there and there. I don't have many domains, I have one domain. And so the domain would have to be, the derivative only exists for times greater than -4. Okay. Anywhere else we'll have a problem somewhere. You follow?
I need the -4 again.
The original -4 came from the root. I can't have a negative in the root, so it had to be -4.
Okay.
But it could equal because square root of 0 in the numerator is all right. We disregarded the equal to here because it ended up in the denominator of the derivative. Okay? Okie dokie. In terms of position, velocity, and acceleration, these are more used in physics than math. Math people would generally prefer to use a parametric set of equations than vectors, but whatever, at least I would anyway. But they will be frequently used in physics, and so you need to be aware, and there's going to be a ton of similarity. So I give you, this time I'm given, this is the velocity vector. Sorry, I didn't denote it, but I'm giving you the velocity vector v, which they would generally tell you, this is velocity now, it's not just some v, it's velocity vector. And I give you a position vector. Now this is an initial condition velocity vector. Position isn't always 1, 3, it's only 1, 3 at time t1 of 1, okay? We want to find position and acceleration. Well, the position vector, this vector v is the change in position horizontally and the change in position vertically. So if I want the position vector, I need just the x and just the y as functions of time. So I must integrate, right? For the x as a function of time, you have an antiderivative and an initial condition. By this time you know there's 2 ways to go about this. You could use an indefinite integral, get a plus c, and use the initial to find the plus c. You with me? You could also use a definite integral, use the initial condition plus a definite integral up to t. Which way do you want to go? Second. Okay. Do you agree that the initial condition for x, now keep in mind this is when time is 1, x is 1, and when time is 1, y is 3 is what's implied by that. Okay, so keep that in mind. So I'm trying to find x. So what goes here? What's the initial condition? I'm starting with a 1 there, and I'm going from when to when? 1 to 2? Oh, you said t. Sorry. T to sometime t. And I'm integrating 3 I don't like square. Don't use x, it's already taken. Let's use something else that's not taken, like u or something, right? So, don't be variable of some sort. Antiderivative? U cubed plus u from 1 to t, that's 1 plus t cubed plus t minus 1 cubed plus 1. So what is the horizontal function of the vector? T cubed plus 2, plus t, excuse me, t cubed plus t minus 1. All right, that is the horizontal function that gives me position at any time on my position vector. Now do the same thing for the vertical component, please. Bless you. Somebody shout out their antiderivative.
3 plus 1.
1 over pi sine of pi. So what'd you get? Y is 3 plus 1 over pi sine of pi t minus 0, right? Okay, that is the other component to your position vector. So if I asked you what's position at time 5, you could just plug time 5 into those and re-roll it, right? What if, about the other question, find acceleration, the acceleration vector. Take the derivative. What's the horizontal component to the acceleration vector? 6t, and the vertical component to the acceleration vector. You get pi sine pi. Okay, easy enough. And then if they wanted acceleration at 2, then you could just use that at 2. All right, last but not least, motion, speed, and distance. Tying it all together, lots of different levels. Say you wanted just basic linear movement. Speed is velocity without direction, right? So how do you remove direction in one-dimensional movement? Absolute value, okay? Now, speed and distance go hand in hand. Velocity and displacement go hand in hand because they use the sign, they use direction. Speed and distance go hand in hand because they don't use direction. So distance is the integral of velocity, of speed. And you're just accumulating how much speed times time total happened, and that tells you how much distance happened. Eh? That's linear movement. The same is true, but a little more complicated in rectilinear or two-dimensional movement. Speed then is still the absolute value of velocity, but now instead of going linearly, you're talking about 2 dimensions. I still want to know how fast it's going this way without direction, and I do that by using Pythagorean theorem and making many small little calculations, right? So the speed is, it's still velocity without direction. And that's the hypotenuse in essence. Speed is the hypotenuse of the velocity calculations. The distance then is just like before. It's the integral of velocity, or the integral of speed. I keep saying velocity. Accumulation of any speed Any calculations? We? Now the new. Okay? Are we good? Now the new part, the velocity vector. You have a vector with x prime, t2 prime, change in position, vertical change in position. Now, speed is still, like I said, parametric and velocity vectors are almost exactly the same. But because they're vectors, how do we show how much velocity in vector form? What do we call that actually? What's the vocabulary? The amount of velocity, who cares about the angle? The magnitude, okay? The speed is the magnitude of the velocity. Now in vectors, we typically write that with double bars. It's the magnitude of the velocity. I don't care about the angle. But it's still the components in the Pythagorean theorem. At least the way the components are changed in the Pythagorean theorem. All right. Would you please get down here that speed is not a vector. It's not a vector because we know vectors have direction, and speed doesn't have direction. Speed is a scalar. It's a number. Okay. Distance then is still, I'd say, that same idea, which we also write in power. All right. So, say you give that first example a go. Please, pretty common question. You should not need a calculator. Go. Have it done in 33 seconds. So what'd you get? Oops, that's not in the right place. What'd you get? It is square root of 144 plus 0, so okay. Alrighty, then the distance, I think, what's the setup for the distance? We don't look at our calculators up. From 0 to 2 of?
6t.
Root 6t quantity squared plus negative pi sine pi t quantity squared with respect to t. Boom. Those are pretty hairy without a calculator. The problem would have to be set up pretty nicely to do without a calculator. Usually they'll be calculated. Okay. Let's go to questions on the homework. 122. 8. 23. 12. 1. 18. Alrighty. Okay. Did you get the original setup like that for 8? And that's the 4 fractions. Alright, so 4 plus 2x. Did you clear the fractions well? So ax squared times x minus 1 plus bx times x minus 1 plus c times x minus 1 plus d x cubed. Okay, you let x equals 0, and you get 4 equals c times negative 1. So c is negative 4. You let x equal 1, and you get 6 equals d. All right, then the hard part comes. Okay. Now, I feel like I can get A, okay, because it has x cubes, and the only other thing with x cubes is d, which I know. So that one will go okay. I feel like A plus d x cubes needs to equal 0 x cubes on the other side. So that implies that A is negative 6. Okay? Now, the last one. All right, I have two choices to find b, either x squareds or x's. Probably the easiest place to go is where there's least of those. Actually, it's pretty fine either way. So, do you want to go with x squareds or x's? X squareds, okay. So, there are negative 6a squareds here. Do you see that? Okay, so negative 6, sorry, x squareds is what I meant to say. Negative 6x squareds and bx squareds and nothing else. So negative 6 plus bx squareds. The other side has no x squareds. So that implies that b must be 6. And you're rolling from there? Okay, well. All right. 23. 23. Okay, use the equation of the segment. Or equation of the line tangent to x. Oh, shoot, that really messed up. xy cubed minus x squared.
Yeah.
Hey, are we? I didn't replace this, right? This is the right problem. Okay then. Well, here we go. Not really feeling it, but okay, here we go. Y cubed plus x times 3y squared dy dx minus x squared dy dx minus 2xy plus 3 equals 0. Okay. These two guys are dy dx-ish, so I'll call it 3xy squared minus x squared dy dx's. And then on the other side I would have 2xy minus 3 minus y cubed. Do you agree with that? Y dx is 2xy minus 3 minus y cubed over 3xy squared minus x squared. Now I want to evaluate that at 2, 1. So, 4 minus 3 minus 1 over 6 minus 4. So 0 over 2? Perfect. So what's your equation? Y equals? 1. Right?
So when x equals anything, it's 1.
Right. That's
That's
dope.
so much work for that.
Yeah, that's dope. Okay. Yeah, that sounds cool. I feel cooler already. I did do that.
I named this right there.
I have teenage daughters. That's dope. Okay. But now that word is dead because of math teacher just said. So, 12. How about 12?
Yeah.
Okay. This part is optional. Do the terms go to 0? On a geometric problem, I don't know if you need to do that because we have other ways of telling if geometric converges or not. If you wanted to do it just by habit of every time doing it, that's good. So make sure you split it and make sure you see the index. Yeah.
You did that first one, where you go to zero.
You wouldn't. All it will tell you is it doesn't diverge usually. Somebody with me so I can continue? Okay. So, this is a geometric with an r equal 1/3. That's less than 1, so it converges. Therefore, the sum is, now be careful, A1 is not 6/3, it's 6 over 27.
Wait, 6 over 2?
Yeah.
Oh, that's what it is. Wait.
This is the sum, got it, it's working already. This is geometric, R is 2/3, which is less than 1, so that converges. Sum is 8/27, and the common ratio is 2/3. Put that together, and you're all good.
Add those answers together.
Yeah, that's the rule of summations. It's the sum of a sum is the same as the sum of two separate sums. That makes sense. Oh, you just put that in your calculator. Yeah, good idea. That's efficient.
If they're the same thing, I can only assume. 16. Yeah.
Oh man, look at those sticky notes.
Okay.
I love those.
I know, aren't they pretty?
They're so cute.
Oh, you can keep
Sticky
those.
notes. My first one is supposed to be 1/3, and the second one's supposed to be 8/9. Yeah, 6 over 27
That's a plus.
times 3 over 2.
Oh, yeah.
Oh, I see.
Let's keep this one for 3/9.
I
Six is 12.
Okay.
I got mine right. Really.
You're right.
Alrighty.
Let's keep it going.
Oh, we have more?
1 and 8.
Alrighty then. Have a nice day. Let's keep it going. That's a good step right there. One.
I got dy equals 9.
Oh, I didn't realize that you did. Yeah.
Oh, yeah.
Oh, right, the series. Yeah.
Yeah. dx dt is a positive. So this is the rate of rates.
Yeah.
2 units per second. They want dy dt when the point is at 2 10 over 3 1. Okay, what'd you do?
Take the derivatives to get dy dx.
The derivative? No. Okay, you're thinking parametric. So that's what this isn't a parametric equation where you find dy dx and divide by dx dt. That's too much. It's a related rates problem.
So you just take the derivative with respect to time.
Exactly. So take the derivative with respect to time. 2 force x dx dt minus 2 ninths y dy dt equals 0. And
I can do it.
plug in everything.
Okay.
That's the spirit. All right. 18. 18. Let's describe the concavity of the parametric curve t squared t sine t at 2. T sine t. Concavity at time equal to.
That's alright.
Okay, ready?
Yes.
Alrighty then. How do I find concavity? Obviously, is second derivative. So let's find the first derivative. Which is
Plus sine t all over t times.
sine of t plus t cosine of t. Is that what you said?
Yeah.
Okay, over.
And then over t e to the t plus e to the t.
Cool. I would sometimes say clean that up, but no, thank you. So let's take the derivative with respect to time of that, but then divide by dx dt. That's how we. All right. So we have a chain rule or a quotient rule, and then divided by dx dt. So here we go. Low d high cosine t plus cosine t minus t sine t. Yes? Oh, boy. Okay. You with me? Minus high d low t e to the t plus e to the t plus e to the t. Wait, all over the square of what's below. All divided by the x dt, which is another t e to the t plus e to the t. Ah, right. You must put yourself on the list. I will require the list.
I made one high. That was
Okay. At 2.
Or you can just open more spots.
I keep forgetting. Besides, I like to discourage people that don't persevere.
No, because what's gonna happen is like up to 40 spots, people are still gonna come and this is.
Yeah, that's what we decided. All right. So, are you ready to go at 22?
Yes.
Okay, so
I'm not trying to find
2e squared plus e squared. Forget this nonsense. This 2b, this is positive. This is 2 cosine, I don't even know if that's positive. 2 cosine t minus 2 sine t.
It was because
I don't know what 2 radians are. 2, that's about 2 radians is about 100 degrees. Oh, but I would even need to know the degree. How much? Oh, gee. Somebody tell me if that's positive. 2 cosine.
Calculate.
2 cosine 2 minus 2 sine 2. Oh, it'll definitely be negative. Never mind, I'm being stupid. Are you kidding?
Oh, I disagree.
No, it's gotta be negative. It's definitely negative. Because that's negative and you're subtracting is positive. It's negative. Done. Okay, this is
Sorry. Positive.
positive and negative. Aye. That one I don't know. Sine of 2 plus 2 cosine 2.
I finished some tests in my screen, so I can
Put yourself on the required list.
you get to take a bite.
So we're going to have to actually see, well, maybe not. All right. So this will be definitely positive. Do you agree? So overall it's negative minus positive, so this must be negative. This is definitely positive. Altogether, then it's definitely negative. Concave down. Concave.
I guess it's not like that one.
Me neither.
right, thanks.
Sure, that was delightful. And by delightful, I mean terrible. All right. Hi, Brian.
Where'd you do that?
Oh, how embarrassing. All right.